Okay, as the final lecture of this week, I plan to a little bit talk about something called spectral gap of a random walk, which I have in the lecture notes in the later in the course, because it's connected to the kind of when we actually use the Fourier analysis to prove something precise. But I'll just define it now to just give you a little bit of motivation how this appears in the Fourier transform. So we call this spectral gap. And so it's defined for probability distribution. So let mu from ZP to C, 0, 1, be probability distribution. Okay, and once we have defined this probability distribution, we can then consider its Fourier transform. So consider the Fourier transform f bar. Okay, so just f bar. So we know that this Fourier transform exists, so we can always compute it using the definitions as we had in the previous lecture. And now we can define the spectral gap to be the following. So we say this mu bar, or this mu itself, has a spectral gap if the absolute value of the Fourier transform is less than 1 for every k in ZP, but not equal to 0. So every other value, but not the ones that are equal to 0. And so let's give you a couple of remarks here. So first of all, if mu is a probability distribution, then the Fourier transform at 0, so the one that we are not considering here, you can always compute it. Remember that this is just by the definition of t equals Zp of mu t e to the power minus 2 pi I 0 t over p, with this just equal to 1. So this is just summation of t in Zp of mu t, but because it's a probability distribution, this is equal to 1. So no matter what we do, we always have the Fourier transform at 0 is equal to 1. So when you look at the spectral gap, this is basically saying that that's the only possibility. The only place where we can have this equal to 1 happens exactly at 0. So now, for example, you can immediately rule out a couple of options. So for example, if you take the Dirac mass at S, if you remember, we computed it in the previous lecture that it's equal to e to the power minus 2 pi I ks over p. So this Dirac mass at k is always equal to 1 for every k in Zp. So this means that no spectral gap. But at the same time, if we take this Fourier transform of this uniform distribution, which we computed to be 1, 0, when k is not equal to 0 and k is equal to 0, so that implies that the Fourier transform of this is less than, this is actually equal to 0 if you actually compute this notation. This is equal to 0 for every k in Zp not equal to 0. So that implies spectral gap. So the spectral gap is a notion that probably should exist for something which is maybe a bit more uniform, more spread out in the space. But then at the same time, let me give you a fourth example. This is kind of like an important example that let's say take this mu, which is equal to a half at Dirac at 0 plus half at Dirac at 2 in Z4. So what we have here is this circle Z4, and we put here a half, and here a half, and then 0 at every other point, 0, 1, 2, 3, this is Z4. Then let's compute the Fourier transform of this one. So what we have here is that the Fourier transform of this at the point k, like we had before, if we compute this just becomes a half e to the power minus 2 pi I k over 4, I think, and then plus half e to the power 2 pi I, plus 2 pi I k over 4. Not k over 4. It's at 2 times. This is, I computed the wrong place. So this is just becomes at the point 0. So this is e to the power minus 2 pi I k 0 over 4, and then you have half e to the power minus 2 pi I, and you have k 2 over 4. So once you open this up, you just get here, this is equal to a half. Actually, I'll open this up half, and this becomes 1 plus, and then you have this expression, 2 over 4, this is equal to a half, so you have e to the power minus pi I k. I think this is what remains. So now what you can see is that this actually, when you compute it as a complex number, this e to the power pi I k, then pi I k, it's always in here. So that's the kind of multiples of minus 2 pi. So this k multiples of this. So if we go on the k, so when k is equal to 0, for example, so you can see that this, if you open this up at the point, so we can see at different points. For example, if you open at point 0, well, this is at the point 0, this is always equal to 1. K is equal to 0. You get 1 plus 1 is half, and k is equal to 0. But then on the other points, you can then compute this at the point, for example, 2. K is equal to 2. You can get here that this is also equal to 1, because now you can get back to the same point at the point 1. And in the other points, I think you can compute this as well, that if you take k is equal to 3 is minus 1, so I think you get 0, and then you get 0 at the other points. K is equal to 1, and k is equal to 3. I think this is what you get. So in particular, the Fourier transform of this, the absolute value, this is equal to 1 when k is equal to 2. So no spectral gap. So you can have something which is not completely concentrated, but because the problem with this mu that you have here is that it's concentrated in this subgroup, this non-trivial subgroup 0, 2 of the Z4. So you don't have a spectral gap in these kind of situations. And then the final thing, a final example you could prove is this: if you take mu is equal to a half, you could take this example 0 plus half 1 in Z4. This has a spectral gap. So this is basically a computation you can do if you want, and with this computation you can see that this has a spectral gap, and that's because it's not concentrated on a subgroup, and then you can see that it will actually have a spectral gap. So using these notations, like if you look at the definition of the spectral gap, so we say that it has a spectral gap if there is this like difference, and we will later on see that this difference, once you have a random walk, will be amplified into something that decays very fast. So the spectral gap allows you to actually have this like mixing, for example, in very fast mixing. And that's why in many situations, the only thing you need to check whether you have, like, for example, mixing of the random walk, whether it has a spectral gap or not. And if it doesn't, then you don't have this kind of like a rate. And the rate of mixing then can then be computed from this, how far from the number 1 your mu is. And then maybe as a final like a remark that I want to maybe mention before the end is that why is it called a spectral gap will come evident in the actually exercises we have in the course. But basically it means that you could talk about as an operator theoretically the transfer operator we talked about earlier in the course. And that transfer operator has something called a spectrum, like the eigenvalues of this operator. We will talk about that in the tutorial, for example, you see. And that actually then you can see that there is a gap in the spectrum. So the spectrum has a gap, and the gap is given by these Fourier coefficients actually, you can, well, from the transfer operator. So that's why the name spectral gap, it comes from the transfer operator and spectrum, whether it has a spectral gap. Okay, so that's all for today. Thanks.